Hello students, today we will discuss about microwave spectroscopy. So as we have seen, microwave spectroscopy is the study of rotating molecules, or the rotation of the molecule will lead to an interaction with the electromagnetic wave will lead to a spectrum in the microwave range. So the rotation of the molecule as such is a very complicated thing. You can see here it is a water molecule which is represented in the picture, and it can rotate about any of its directions. So as such, a rotation, if you consider, it is a very complex thing to deal with. So for simplicity we will resolve such a rotation into three mutually perpendicular directions. So these are the directions. You could take it in along the plane of the display, or it could be along the rightward side, or it could be towards you, that is in the y direction. So these are the three mutually perpendicular directions we know in the Cartesian coordinate system. So we'll restrict our motion or rotation about only these three axes, okay, which are perpendicular to each other. So if you consider in such a way, this particular water molecule can rotate about an axis in the z direction as shown. So z direction means it is the direction along the plane of the display unit, so which means the molecule will be rotating about like this. The other direction possible is like this, which is in the x direction. So the molecule will be rotating about this axis, and the other one is the axis is perpendicular to the display unit, or you can say the axis is towards you. So then the molecule will be rotating like this. So these are the three possible rotations when you restrict a discussion only to only in terms of three axes along. Okay, so such a thing is represented here. So where you can see, let me see. So this one is about the axis, and this rotation is about the so you can see this kind of rotation is about an axis like this. Okay, so about this one. Okay, and if you look this one, this is moving towards you, which means the direction of the axis is like this. So then the molecule will be rotating like this. Okay, so let me point it out. So in the first case, this way it is moving about this axis, and this one it is moving around this axis. Okay, and the third possibility is that it is rotating about this axis. So these are the three possibilities when you restrict your discussion only to the three mutually perpendicular directions. So let us observe it for another molecule, that is a diatomic, a very simplest molecule, where we have we have three axes shown, x, y and z directions. So here we can see about the vertical axis. Let me consider the diatomic molecule like HCl, which is a linear molecule. So you can see it is rotating about this axis shown by the dotted line. And another possibility is that the molecule is rotating about this particular axis. So in this case it is called molecular axis, which is along the bond axis, and hence this kind of axis is called molecular axis of the molecule. And the third one is the axis is perpendicular to the display, so it is just rotating about the axis. So these are the three possibilities of rotations in the three mutually perpendicular axes along. Let me show it again. One is about the z axis, the other is about the x axis, which is also called molecular axis, and the third one is along the y axis, which is actually perpendicular. So the second and the not the second, I mean the first one is an end over end rotation. Okay, the ends are getting changed. And the third one is also an end over end rotation, while in the case of the second one, that is about the molecular axis, it is not an end over end, it is just rotating about its place itself. The atom is the chlorine atom is rotating about that place itself, and hydrogen is also rotating about that place alone. While in these two cases, one and third cases, you can say they are said to be end-over-end rotation, because you can see hydrogen will be coming this way, then chlorine will be coming this way. So they are exchanging the places. So here also chlorine will be coming this way and hydrogen will be coming this way. Okay, so that is also another end over example for end over end rotation. Okay, so corresponding to those, we can mention, since the rotation are represented about three axes, you can consider moment of inertia about these three axes. So these are the three principal moment of inertia. One is called IA. IA is about the molecular axis, moment of inertia about the molecular axis, and IB and IC are the moment of inertias for the end over end rotations. Okay, so this is the moment of inertia about this axis will be represented as IA, and the other ones could be IB or IC. Okay, so based on the moment of inertia, so why we are saying about the moment of inertia is that we'll be classifying the molecules based on what are the values of IA, IB and IC, the moment of inertia is about the three mutually perpendicular axes. Or you can say it is similar to classifying the molecule on the basis of shape of the molecule. So in either of the way you can put it in. And the first one is linear molecules. So linear molecules, example is, you can say HCl, as we had just seen. So here IA is along this direction, IB is along this direction, and IC is along the perpendicular axis. So these are the three mutually perpendicular axes possible. So here you can see, if the atom rotates about the molecular axis, what happens? There is no about the atoms are placed along the axis. So for moment of inertia, you know the expression as it is mass into r square, where r is a perpendicular distance of the mass from the axis. So if you check along this particular axis, let us consider it A axis, the masses or the atoms are arranged along the axis itself. Nothing is extended beyond the axis. So what about the r? R will be 0. The perpendicular distance of the mass from the axis is 0, because they are lying along the axis. So the moment of inertia for a linear molecule will always be 0. While if you check IB and IC, which are the moment of inertia along B axis and along C axis, we can see the masses are equally distributed about, or the appearances for B axis and C axis will be the same. So IB and IC will be always equal. So such kind of molecules are said to be linear molecules, or you can say it is due to the linear appearance they have a moment of inertia of this kind. Okay, either of the way you can put it. So that is a one kind of molecules. And the second kind of molecule is symmetric top molecule, where you can see IA is not 0, it is a non-zero value, but two possibilities could be possible. Either IA can be greater or IA can be less than the other two moment of inertia. So if the moment of inertia about B and C axis are greater than the IA value about the molecular axis, such a molecule is called prolate molecule. Example is that of a CH3Cl. We can say Cl is along this one, and carbon is at the center, and H are distributed like the leaves of a fan, 3 leaves of a fan. So it has a symmetric top kind of appearance. And the peculiarity is that about B and C direction, the moment of inertia are the same. So this is the main axis or the main molecular axis. so which we call it as a axis. So the moment of inertia about a axis is denoted as IA, and the other mutually perpendicular axes are given by B and C axis. Okay, B and C axis. So in about the B and C axis, the distribution of masses about the axis are the same. That is why IA and IB are the same. Why along IA it is in a different way. You can see chloride ion is along the molecular axis, carbon is also along the molecular axis, and hydrogen are distributed about the axis. So it is only the difference in position of hydrogen from the axis will lead to a very small moment of inertia about the molecular axis, that is A axis, while here nothing was extended outward, that is why IA was 0. Here there is a very small value for IA. Okay, so remember the equation, it depends upon mr square for the moment of inertia. Now consider the second case where the IA can be greater than the IB or IC value. So in that case the molecule is called oblate molecule, and example is boron trifluoride, where you can see it is like the leaves of a fan, planar ആയിട്ടുള്ള molecule ആണ്. So where you can see this particular axis IB and IC and IA, you can see it has IA has a greater moment of inertia. And in the third kind of molecule, it is spherical top molecule, where you can see all the moment of inertia are having equal value. An example is CH4, where you can see that in whatever direction you will take, they will appear in a similar manner, and hence it will give a equal kind of moment of inertia. Okay, but in this case you cannot consider in that way, because if I take along this direction, the one mass is less here and here two masses are there, so the moment of inertia will be always different. The mass on one side is greater, and hence that is why there is a difference. Okay, while if I rotate along this direction, you can see there are symmetric arrangement. If I rotate about this axis, there is also symmetric arrangement. So that is why IB and IC are the same while IA is different. While in the case of CH4, in whatever direction I take the axis, whatever three mutually perpendicular directions, all the directions will give a similar appearance for the rotation, and hence the similar moment of inertia. And the last one is asymmetric top molecules, where all the moment of inertia are different or unique, and example for such a most of the molecules are asymmetric top molecule. They doesn't have any preferential molecular axis, and they will have moment of inertia different along all the three mutually perpendicular directions. So these are the four classifications of molecule based on, you can say, moment of inertia or based on the shape. So I'll end with this. Thank you.